All right, let's take a look at the practice test. For the instructions, we're asked to find the domain and range. Before we get started, the first two problems are going to involve finding the domain and the range, but then we're going to get into some harder problems that just ask us for the domain. That's typically how this section is going to work. Your easier problems involve finding the domain and the range, and then you start getting into more complicated things and they'll just ask you for the domain. So when we ask for the domain of a relation, or it could also be a relation that's a function, basically what you're asking for is what real numbers can I plug in for the independent variable, in most cases it's going to be x, that's going to produce real numbers. So you always want to think about this in terms of the real number system. So the first thing is that I would think about when you consider your domain, you can't divide by 0. So you're going to have a lot of fractions that are thrown at you. Always think about, well, what would make my denominator 0? The second thing is, in the real number system, you can't take an even root, so a square root, fourth root, sixth root, something like that, of a negative number. So for example, if I had something like the square root of -9, using only real numbers, there's not a number that I could square that would give me -9, right? Because squaring something gives me a non-negative result. So using real numbers only, the square root of -9, you would say that's not a real number. If we use the imaginary unit I, then of course we can work with that problem and say that it simplifies to be 3i, but we're not on that in this particular case. Then down here we say the absolute value, and then also the squaring operation always gives a non-negative result. So something else you want to consider. All right, let's take a look at the first problem. So here we have y is equal to -3x minus 2. The first thing I'm going to do is just copy this. So y equals -3x minus 2. I'm just going to grab this real quick, and I'm just going to come down here to the graph. I think it's very helpful when you solve these problems to have an idea of what this looks like. So the first thing is when we consider the domain, we are thinking about what is possible in terms of the real numbers that can be plugged in for your independent variable. In this case, it's going to be x. So you want to be able to plug in some real number here and then go through what's given. So in this case, it would be multiplied by -3, and then that product would have 2 being subtracted away from it. You want to think about, would that give me a real number? So plugging in a real number, would I get a real number? Well, thinking about this, I can plug in a negative, I can plug in 0, and I can plug in a positive, right? You can look at the graph and see that. We have these arrows here that are telling us that this is going to extend indefinitely to the left and to the right. So we would cover the entire set of real numbers. And you can try a few values out. So let's say we tried an x value of, let's say -1, just to use something that's negative. Well, y would be equal to -3 times -1, then minus 2. So -3 times -1 is 3. So this would be 3 minus 2, which would be 1. So if x is -1, y is 1. So that's going to be this point right here. That's on the graph. Now you could try 0. So that would give you your y-intercept, right? So if you plugged in a 0 for x, let me do that real quick. So y is equal to -3 times 0 and then minus 2. Of course, -3 times 0 is 0. So this would be 0 minus 2, which is -2. So that gives you this point right here, which is 0, -2. And then lastly, you could try some positive value. So let's just say that we pick an x value of 2. So let's say y equals -3 times 2, and then minus 2 like this. -3 times 2 is -6. So this would be -6 minus 2, which is -8. So let's go 2 units to the right and then 8 units down. So that would be right there. That would be 2, -8. All right, so we can see clearly that you could plug in any negative that you want, 0, or any positive that you want. So basically for the domain, you would say it's the set of real numbers. So let me actually write that out. So we'll say that the domain is going to be the set of all x such that x, we'll just say, is a real number. Now, if you wanted to write this in interval notation, some people prefer that, you could say it's from -infinity to +infinity. Now, what about the range? Well, given the fact that I can plug in whatever I want for x, that means I can get out whatever I want for y. I can make it as small as I want, I can make it 0, or I can make it as large as I want just by changing the value that I plug in for x. So let's go ahead and say that the range, so the range is going to be the set of all y such that y is a real number. And then additionally, you could write this in interval notation, so from -infinity to +infinity. All right, let's take a look at problem 2. So here we have y is equal to the square root of x plus 1 minus 3. So again, I'm going to look at the graph with you. I think it's very helpful for these types of problems. Let me just arrow to this real quick and say that this is y is equal to the square root of x plus 1, and then you have minus 3 here. Okay, so the first thing is when you consider the domain, if you look at the graph, you can see that the furthest x value going to the left, okay, so this is going to be the smallest x value, that's going to occur where x is negative 1, right? So this point right here, let me highlight it. This would be negative 1 comma negative 3. So what is causing that? Why don't we have values that go to the left of negative 1 on the x-axis? Well, basically, again, when you think about the real number system, you can't take the square root of a negative number. So here you would think about the fact that I have the square root of x plus 1. So what can I plug in for x there? What I would say is that x plus 1, or the radicand here, the part underneath the square root symbol, needs to be non-negative. So you would say this is greater than or equal to 0, because it could be 0 or some positive number. So we're going to solve this simple inequality, just subtract 1 away from each side of the inequality. And so let's go ahead and cancel this guy right here, and we'll say that x is greater than or equal to negative 1. Now you can verify that on the graph. X is negative 1 at the smallest, and then it's anything larger, right? So going out to positive infinity. So you can go ahead and say that for the domain, let me write this up here. So for the domain, it's going to be the set of all x such that x is greater than or equal to negative 1. Again, you can also write this in interval notation if you prefer that. So you want to put a bracket next to negative 1 to show that negative 1 is included. And then you're going to go out to positive infinity. Make sure you always use a parenthesis with infinity. And basically, let's think about the range now. So looking at the graph, you can see that the smallest value for y, or the lowest point on that graph for y, is going to occur at negative 3. Right? So you see this is negative 1 comma negative 3. The y value is negative 3. So why is that the case? Well, again, if we consider our domain restriction that x needs to be negative 1 or larger, if I plugged in a negative 1 for x, negative 1 plus 1 would be 0. So you'd have the square root of 0, which is 0, and you would just get y equals negative 3. So basically, that's as small as you can get y to be. Any value for x that you plug in that's larger than negative 1 is going to produce a larger value for y. And this would be true. You can keep plugging in bigger and bigger values for x as far out to positive infinity as you want. So you can make y as large as you want going out to positive infinity. So you would say that the range is going to be the set of all y such that y is greater than or equal to negative 3. I think this could be written a little bit cleaner here. Let me make this negative 3 cleaner in case you're looking at that. And still didn't really get that, so let me make that a little bit better again. So then if you wanted to do this in interval notation, now you're going to put a bracket next to negative 3, so that's going to be included, and you would go out to positive infinity. All right, for the next few problems, the instructions are going to change. So now we just want to find the domain. We don't need to find the range for these examples. For problem 3, we are given that y is equal to 2x over, you're going to have the absolute value of 3x minus 3, and then minus 6. So again, when we think about the domain, we're thinking about what real numbers can we plug in for the independent variable, in this case, x. Remember, we can never divide by 0. So I would think about my denominator here, and I would just set it equal to 0, and I would solve, and then those solutions are going to be restricted from the domain because they result in a denominator of 0. So we're going to say that the absolute value of 3x minus 3 and then minus 6 is equal to 0. So let's solve this real quick. Hopefully you remember how to solve a simple absolute value equation. What you want to do is isolate the absolute value operation on one side, and you want to get a single number on the other. So we're going to add 6 to both sides of this equation. We're going to cancel this away. So now you're going to have the absolute value of 3x minus 3 is equal to 6. So now that we have the absolute value operation isolated, you want to set up a compound equation with OR. So you're going to take this expression inside the absolute value bars, and you're going to say that 3x minus 3 could be equal to 6, or 3x minus 3 could be equal to negative 6. Because if the result of this was 6, based on what you plugged in for x, well, the absolute value of 6 would be 6. And then if the result of this, based on what you plugged in for x, was negative 6, well, again, the absolute value of negative 6 would be 6 as well. So you need these two different equations. All right, so for this one on the left, let's add 3 to both sides. Let's go ahead and cancel this. And we'll say that 3x is equal to 6 plus 3 is going to give me 9. Divide both sides of the equation by 3, and you're going to get that x is equal to, let's cancel this, 9 over 3 is 3. On this side, let's add 3 to both sides of the equation. Let's cancel this away, and we'll say that 3x is equal to negative 6 plus 3 is negative 3. Let's finish this up by dividing both sides of the equation by 3. This would cancel, and we're going to say that x can also be negative 1. So coming back up here, we want to make sense of what we found. We said that x equals 3 or x equals negative 1. Let's remind ourselves of what we're trying to do. We're trying to figure out where this denominator would be 0. So it's going to be 0 when x is 3 or if x is negative 1. So those values have to be restricted from the domain because we can't divide by 0. If you plugged in a 3 here, you would have 3 times 3, which is 9, and then 9 minus 3 is 6. So you would end up with the absolute value of 6, which is 6, minus 6, which is 0. Right? So you'd have 0 in the denominator, and again, division by 0 is undefined. The same thing would happen with negative 1. If you plug that in there, 3 times negative 1 is negative 3. Negative 3 minus 3 is going to be negative 6. And so the absolute value of negative 6 is 6. So again, you get 6 minus 6, which is 0. Division by 0 is undefined. So let's set this up, and we'll just say that for the domain, it's going to be the set of all x such that x is not equal to, let's put negative 1, and then also 3. Now, you can also write this in interval notation if you wanted to, but it's going to be a bit lengthy. So basically, you would come from negative infinity and go up to and exclude negative 1. And then the union with, you would exclude negative 1 again, and you would go up to and exclude 3. And then the union with, you would exclude 3 and go out to positive infinity. I think this right here using set builder notation is much cleaner, but some people want to answer that way, so that's really up to you. Basically, this covers the whole number line except for negative 1 and then also positive 3. All right, so to visually see what's going on here, you can always sketch the graph. So I recommend this when you first start doing these problems. You can go to any online calculator and just type in y equals 2x over the absolute value of 3x minus 3 and then minus 6. You're going to see that you get the same result visually that we got from setting the denominator equal to 0 and solving the resulting equation. Basically, when you look at the graph, you see that you have a vertical asymptote at x equals negative 1 and then a vertical asymptote at x equals 3. So in each case, what's happening is, if you look at this piece of the graph here, this graph is approaching an x value that's going to be negative 1, but it's never going to actually get there. Same thing coming from this guy, so it's approaching an x value of negative 1, but it's never actually going to get there. So you can't actually have an x value of negative 1. Then here, you're approaching an x value of 3, and over here, you're approaching an x value of 3, but you'll never actually get there. So the graph is consistent with what we found, that the domain is the set of all x such that x is not equal to negative 1 or 3. All right, let's take a look at problem 4. So here we have y is equal to 5x minus 3 over the square root of the absolute value of x squared plus x minus 2, and then minus 4. So when you think about the domain for this type of problem, in the numerator, you're not going to have any issues. You just have 5x minus 3. When we move into the denominator, that's where you have to consider division by 0, and then also this square root operation. So first, let's think about the square root operation. When we have a square root and we're working in the real number system, we can't take the square root of a negative number. So that means the radicand here needs to be non-negative, or you could say greater than or equal to 0. So let's start by saying the absolute value of x squared plus x minus 2, and then minus 4 needs to be greater than or equal to 0. But there's a problem with what I just wrote here. If you're in the denominator, you cannot divide by 0. So let's say I have the square root of 0. Well, that would be 0, and then I'd have division by 0, which is undefined. So you have to make an adjustment here because you're in the denominator. So we would say the absolute value of x squared plus x minus 2, then minus 4 is strictly greater than 0. So before we solve this inequality algebraically, let's look at the graph. So if you take the left side here of this inequality and you type that into Desmos, so the absolute value of x squared plus x minus 2, and then minus 4, you could put y equals in front of that if you want. It's going to give you the same graph. Basically, what you're trying to do is figure out what are the x values that are going to produce y values that are greater than 0. The place I would start here, I would think about the x-axis. So that is the horizontal line, y equals 0. So on the x-axis, we know the y values are 0. So let's look at this point right here to start. So this is an x-intercept, so -3, 0. Again, we're on the x-axis. And this is another x-intercept. So this right here would be 2, 0. Again, we're on the x-axis. So if we think about x values that are to the left of -3, what do we see in terms of the y values? Well, they're going to be greater than 0, right? So we are above the x-axis. Additionally, if I think about x values to the right of 2, or you could say greater than 2, well, we are, again, above the x-axis in terms of the y values. We're greater than 0. Okay, so putting a solution together from the graph, I could really say that this guy is satisfied when x is less than -3, then or when x is greater than 2, right? We can see that. At -3 or at 2, the y value is 0, so that's not going to satisfy the inequality. And then between those two values, the y values are going to be less than 0, right? So that's not going to work. So this is what we would expect for our solution. Let's go ahead and grab this. All right, so let's do this algebraically. What I'm going to do first is think about a rule that we learned a long time ago. Let me write this off to the side. So if you have some algebraic expression, let's call it u. In this case, that's going to be the x squared plus x minus 2 that's inside the absolute value bars. And let's say it's greater than some positive real number. Let's just call it k. Well, the way this sets up is that u is greater than k, or u is less than -k. So we're going to just use that rule here. I'm going to add 4 to both sides of the inequality. So let me go ahead and say that this is greater than 4. And then I'm just going to set this up here, this compound inequality with or. So let's say we have x squared plus x, then minus 2 is greater than 4. And then I'll say or, we're going to have x squared plus x minus 2 is less than -4. Okay, at this point, we don't even need this anymore. I'm going to get rid of this. We know how to solve a quadratic inequality. Basically, you want the right side to be 0, and then you want to get your critical values by replacing the inequality symbol with equals. And then you take those critical values, you set up some regions on the number line, and you're going to use some test points. So let me go ahead and subtract 4 away from each side of this inequality. So let me do that here visibly. So this would be a -6 here, and of course this would be 0 here. And then let me do the same thing here. Let me add 4 to both sides. So this right here would be a 0, and then -2 plus 4 is going to be a 2. Now, you're going to find that this one doesn't have a solution, and I'll get to that one momentarily. Let me start with this one, which is a little bit easier. So let me write x squared plus x minus 6 is greater than 0. So let me grab this real quick, and let me come down here where we have our little number line set up. So the first thing I would do with this is factor it. So let me put a little 1 right here, and I'm going to factor the left side just to make it a little bit easier. So put an x here and an x here. Give me two integers whose sum is 1 and whose product is -6. So you can do a +3 and a -2. So 3 times -2 is -6. 3 plus -2 or 3 minus 2 is 1. Now I'm going to get rid of this version here. I'm just going to stick with the factored form. And basically at this point, you would want to replace the inequality symbol with equals, right? So you would have x plus 3, that quantity, times the quantity x minus 2 is equal to 0. And you're going to use your zero products property. And basically you're going to say that x plus 3 equals 0, or x minus 2 equals 0. Again, this is us finding the critical values, or where this guy is going to be 0 on the left side. So what I would do here is subtract 3 away from each side, and so you would get x is equal to -3. Over here, I would add 2 to both sides, and so you would get x is equal to 2. So let's put our -3 here, and let's put our 2 here, and then you can get rid of all of this. You don't need it anymore. Let me rewrite that in. You can get rid of this. Now we're just focused on the inequality. So I like to label this as region A, B, and C. Region A is anything less than -3. B is between -3 and 2, and C is greater than 2. So just pick a value in that region. Okay, it can't be the critical value itself. So for A, I would pick -4. So I'm going to plug in a -4 there, and then a -4 there. And then basically a lot of people will just do a sign analysis. So they'll say, okay, well, -4 plus 3, let me do this off to the side, a little border. -4 plus 3 is going to be -1. And then -4 minus 2 is going to be -6. What they do is say they have a negative times a negative, which is a positive, and a positive is always greater than 0. So they don't need to really evaluate this. They just go ahead and say, okay, well, this is going to be true. But you can go through and say -1 times -6 is 6. And so basically you would have 6 is greater than 0. And so that's a true statement, right? So either way you want to do it. For this one in region B, I would pick 0. So you're going to plug that in there and then also there. So you'd have 0 plus 3, which is 3. And then times 0 minus 2 is -2. Again, a lot of people are just going to say positive times negative is negative. A negative is never greater than 0. So this is false. But you could also say 3 times -2 is -6. And so you would get -6 is greater than 0, which is a false statement, right? So this is false. All right, the last one for region C, I would pick maybe 3, plug that in for x there, and then also there. 3 plus 3 is 6, and then 3 minus 2 is 1. Again, positive times positive is positive, and so that's always greater than 0, so this is true. But again, you can always go 6 times 1, which is 6, and just write out that 6 is greater than 0, right? That's a true statement. Okay, so we've found our solution. Let me get rid of this. This is a strict inequality, so -3 and 2, those are excluded. So basically, you would just say that x is going to be strictly less than -3, or x is greater than 2. So let me come back up here, and I'm going to paste this in right here. This is my solution for this. Let me show you this real fast in case you are interested. So if you go to Desmos, again, only type in what's on the left-hand side. So x squared plus x minus 6, or you can go y equals x squared plus x minus 6. You're looking again for the x values for which the y values are greater than 0. So if you see again, anything that's to the left of -3 would give you a y value that's greater than 0, and anything to the right of 2 in terms of the x values would give you a y value that's greater than 0. So x is less than -3 or x is greater than 2. Now, for this other one, you're going to have a problem. I'm just going to write for right now that there's no solution, and I'm going to prove that to you. So for this one, it's going to be a prime polynomial for the left side. If you think about x squared plus 1x plus 2, if I say give me two integers whose sum is 1 and whose product is 2, you're not going to be able to do that. Right? 2 is a prime number. It's only 2 times 1. And if you're adding 2 and 1 together, you're going to get 3. So this is impossible. So what you would do here is use your quadratic formula. So this is A, this is B, and this is C. So for the quadratic formula, it's x is equal to the negative of B plus or minus the square root of b squared minus 4ac, and then all over 2a. Well, let's plug things in and see what's going on. So for the negative of b, b is 1, so this is -1. Then b squared, well, 1 squared is 1. And then a is 1. You can get rid of it if you want, or you can write it in. It doesn't matter. 4 times 1 would just be 4. And then for c, it's 2. So let's plug in a 2 there. Okay, so you have 4 times 1, which is 4, times 2, which is 8. Let me put this here. So you have 1 minus 8, which is -7. And really, I'm just going to simplify this to say that the square root of -7 is going to be I times the square root of 7. Down here, you have 2 times a is 1, so just erase that. 2 times 1 is just 2. So when you get this situation where you're trying to find your critical values, in other words, we take this guy, we set it equal to 0, and we solve it. Here we use the quadratic formula, and you get two non-real complex solutions. What that is telling you is that you're not going to have any x-intercepts. So that means the graph is never going to cross the x-axis. So it's either always above 0 in terms of the y values, or it's never above 0 in terms of the y values. So it's either always true or never true. So you either get all real numbers for the solution or no solution. So how do you figure out what the solution is? Well, first off, you could graph it, right? So let me do that first. Again, thinking about this, here is x squared plus x plus 2. So you just want to type this, or you can put y equals x squared plus x plus 2 into Desmos. You're going to get this graph here. You see that it does not impact the x-axis. So there are no x-intercepts in this case. So what's happening is you're asking, where are the y values less than 0? Well, they're never less than 0. Less than 0 would be below the x-axis. That's never going to happen, okay? If you flip this around and you said, where are they greater than 0? Well, it's always going to be greater than 0. So where are they above the x-axis? Always. Okay, so the y values are always greater than 0. But here we have a less than, so this is never going to be true, so there's no solution. So if we come back up, we have no solution there. Now, algebraically, if you don't want to make a graph, not that big of a deal. If you see that you get two non-real complex solutions when you try to set up your equation and solve for the critical values, all you have to do is pick any number, it doesn't matter what it is, and just plug it in and see if it works. If it does, then all real numbers. If it doesn't, then there's no solution. You could pick 0, it's easy to work with. So you would have 0 squared, which is 0, plus 0, which is still 0, and then plus 2, which is 2. So you would get 2 is less than 0, which is false, right? So there's no solution. So we don't have to worry about this. we only have to take the x is less than -3 or x is greater than 2, which we found originally by looking at that graph where we had the absolute value of x squared plus x minus 2 and then minus 4, right? So we looked at that immediately and said, well, where are the y values greater than 0, where it was where x was less than -3 or x was greater than 2. And a lot of you will ask, well, why did you go through all that algebra to come up with the same thing you found in a few seconds from the graph? Well, not everybody's going to be able to graph that stuff, and maybe you have to show this algebraically for your teacher, so it's good to just get some practice with things. Okay, so we're just going to write out the domain. So let's write out the domain. We would say that this is the set of all x such that x is less than -3. Then I'll just put a comma. So we're also going to say that x could be greater than 2. So x could be less than -3 or x could be greater than 2. Okay, so let's put this like this. Let's get rid of this. And we could write this in interval notation. So coming from -infinity, going up to and excluding -3. So we're going to use a parenthesis there. And then it would be the union with, you would have anything greater than 2. So 2 would not be included, so use a parenthesis there. So this is out to infinity. All right, let's wrap things up and just come to a little graph. And what we see will confirm what we have here. So if we look at y equals 5x minus 3 over the square root of the absolute value, let me make that more clear. So the absolute value of x squared plus x minus 2 and then minus 4, well, what's going to happen is you're going to have a vertical asymptote here at x equals -3. And you can see that this guy is going to approach an x value of -3 but never touch it. But it could be anything going to the left. So any value that's less than -3, you're okay. And then over here, you have another vertical asymptote at x equals 2. So the graph would approach an x value of 2 but never touch it. And again, going this way, it can be anything, right? So going out to positive infinity. So this confirms our domain. We have the set of all x such that x is less than -3, or x could be any value that's greater than 2. All right, let's take a look at problem 5. So now we have y is equal to the negative of 7 over x squared minus 4x minus 5. So again, if I'm working with a fraction, I'm thinking about division by 0. And so this denominator here, which is x squared minus 4x minus 5, I would just set that equal to 0 and solve the resulting equation. So the solutions here, we're going to restrict that from the domain because, again, that would just make the denominator 0. So a simple quadratic equation to solve. The first question is, can we factor this? So let's go ahead and try that real fast. I'd put an x here and an x here. And then I want two integers whose sum is -4 and whose product is -5. Well, what I could do is -5 and then +1. So 1 plus -5 would be -4. And then 1 times -5 would be -5. So this is the correct factorization. So this is pretty easy to solve. You would just say x plus 1 is equal to 0. Then or x minus 5 is equal to 0. We would subtract 1 away from each side of the equation, cancel that, and get x is equal to -1. Over here, let's add 5 to both sides of the equation, cancel that, and say x is equal to 5. So we would restrict -1 and then also 5 from the domain. So coming back, let's write out that our domain is going to be the set of all x such that x is not equal to -1 or 5. Again, let's do interval notation in case you're interested in that. So you would come from -infinity and go up to and exclude -1. And then the union with, you'd put -1 as being excluded, going up to and excluding 5. And then the union with, you would exclude 5 and then go out to positive infinity. So basically the whole number line, you're just excluding -1 and you're excluding 5. So once again, just coming to the graph, we have y equals -7 over x squared minus 4x minus 5. And looking at this, you can see that x is not going to be -1 or 5 from the graph. Again, you have a vertical asymptote at x equals 5, and then another vertical asymptote at x equals -1. So your graph is going to approach an x value of -1, but never touch it. And your graph is going to approach an x value of 5, but never touch it. All right, let's take a look at problem 6 now. So here we have y is equal to, we have the negative of x minus 2 over x squared minus 5x plus 6. So let's come down here real quick. Now, the trick here is to immediately just set the denominator equal to 0 and solve that. When you have a rational expression, remember, when you think about the domain, it's always going to be in terms of the original rational expression. A lot of you are looking at that and you're going to try to simplify it and you're going to end up with the wrong answer. So let me do it the correct way first, and then I'll show you the common mistake. So first, I'm just going to grab this denominator here, and I'm going to set it equal to 0. So I'm going to say x squared minus 5x plus 6 equals 0. So let me slide down here, and I'm just going to solve this with factoring. So I'm going to put an x here and an x here, and give me two integers that sum to -5 and have a product of 6. So that's going to be -2 and then -3. So by the zero product property, you could just say x minus 2 is equal to 0, or x minus 3 is equal to 0. We could add 2 to both sides of the equation here and cancel that and say x is equal to 2. Over here, I can add 3 to both sides of the equation, cancel that, and then we'll say x is equal to 3. Okay, so x can't be 2 or 3 because that would give us division by 0. So let me go ahead and get rid of this. And let me write out the domain first, and then I'll show you the mistake that a lot of people make. So let's say that the domain is going to be the set of all x such that x is not equal to 2 or 3, okay? And again, you can put this in interval notation if you want. You can just say from -infinity going up to and excluding 2, and the union with, you're going to go from 2 to 3, and you're going to exclude both, and the union with anything larger than 3. So again, I like this form better. It's just cleaner, more concise. This one right here is kind of a mess when you start getting into things of this length. The common mistake, let me just write this. So y is equal to the negative of x minus 2 over, you have x squared minus 5x plus 6. You saw me factor this, and we got the quantity x minus 2 times the quantity x minus 3. So let me set this up as the quantity x minus 2 times the quantity x minus 3. Okay, so what do most people do? They're going to say, okay, well, I can cancel this with this. And so this becomes the negative of 1 over x minus 3. So if I look at this expression right here, well, the domain would be the set of all x such that x is not 3. There's nothing stopping me with this expression right here from plugging in a 2. But in the original rational expression, I can't plug in a 2. So whenever you're working on a domain problem and you have a rational expression that can be simplified, you always go with the original non-simplified version to get the domain, okay? It carries itself over even though you can simplify. All right, so coming to the graph here, there's going to be a lot to explain. First off, I would advise you to go to Desmos and type in 2 different graphs. So the first graph, I would type in y equals the negative of, you have x minus 2 over, and you can put this in factored form or non-factored form. So you can go the quantity x minus 2 times the quantity x minus 3, or you can say x squared minus 5x plus 6, whatever you want to do, it's the same thing. Now, if you were to simplify this, again, cancel a common factor of x minus 2 and write this as y is equal to the negative of 1 over x minus 3. The graph would look exactly the same except for where x is 2. Now you're going to see that if you move your mouse over 2, it's going to say 2 comma 1. Okay, so that's the difference between this form and this form. But again, when you get a rational expression, you always go with the original rational expression, the non-simplified version, if you're asked for the domain. Okay, so I'm just going to get rid of this. And so that's why you have this hole in the graph right there. We're going to talk more about these holes in the graphs later on when we get to rational functions. For right now, we're just thinking about the domain. Okay, so you see that at 2, it's not defined. There's a hole in the graph. Then additionally, this guy that you couldn't cancel away, this x minus 3 that's still going to be in the denominator, you can see that's creating a vertical asymptote here at x equals 3. So basically, the graph is going to approach an x value of 3, going this way and then also going this way, but it's never going to touch it. Okay, so using the graph, you can confirm that the domain is the set of all x such that x is not 2. Again, you've got a hole in the graph there, and then also x can't be 3. Again, you see that vertical asymptote there. All right, let's take a look at problem 7. So here we have y is equal to, we have the square root of x plus 4 over 2x minus 6. Okay, so in this case, you have 2 different things going on. The first thing you have to consider is that in your numerator, you have the square root operation, and your radicand is x plus 4. So you want to make sure that this right here is non-negative. So the first guy, let me just put first, thing that we would consider is that x plus 4 needs to be greater than or equal to 0. That's pretty easy to do. We would just subtract 4 away from each side of the inequality, cancel that, and say x is greater than or equal to -4. Okay, so x can be -4 or anything larger. But you also have to consider your second guy there, which is that this denominator cannot be 0, right? So you would say, well, 2x minus 6, if that was equal to 0, and you add 6 to both sides of the equation, me slide down here for a moment and cancel this. And we would say, let me just drag this over here, 2x is equal to 6. Divide both sides of the equation by 2. Let's cancel that away. And we'll say that x is equal to 6 over 2 is 3. So we would say that the second condition is that x cannot be 3, right? Because again, if you plug in a 3 for x, well, then you're going to have division by 0. Let me get rid of this. And let me pull this up here. And let's combine these two. And I kind of messed up my border there. Maybe we don't need it anymore. Let's combine these two conditions. So first, x has to be greater than or equal to negative 4. And then second, x can't be 3. Okay, so for the domain, let's write out that it's the set of all x such that x is greater than or equal to negative 4. I'm also going to put that x cannot be 3. Okay, so let me close that down. Now, if you want to do the interval notation on this, you put a bracket next to negative 4, and then you're going to go out to a value of 3, and you're going to put a parenthesis next to 3 because it's not included, and then you're going to put the union with, again, the parenthesis goes next to 3 because it's not included, and then out to positive infinity. So that's how you're going to exclude 3. You have a parenthesis here and then a parenthesis here. So basically anything from negative 4 going out to positive infinity with you excluding one number or one value, which is going to be 3. So again, let's take a look at the graph just to confirm what we found. So first off, you would see that we said that x is greater than or equal to negative 4. Okay, well, here's negative 4 right here on the x-axis, and you see that there's no x value to the left of that. So this is your smallest x value, and this point occurs at negative 4 comma 0, right? If you plugged in a negative 4 here, negative 4 plus 4 is 0. 0 divided by something that's not 0 is going to give you 0, so you get negative 4 comma 0. Then you can have any x value that you want going out to positive infinity with one exception. X can't be 3 because, again, if you plugged in a 3 for x, you're going to get division by 0. So that's creating a vertical asymptote here at x equals 3. So the graph here approaches an x value of 3, but again, it will never touch it. And here, the graph is approaching an x value of 3, but it will never touch it. So here, the domain would be the set of all x such that x is greater than or equal to negative 4, and x is not equal to 3. All right, let's take a look at problem 8. So here we have y is equal to, we have the square root of 3x minus 2. This is over 6x squared plus 8x minus 30. Let me slide down here just a little bit. And again, you're going to have two different things that you have to consider. The first thing is you have a square root in the numerator. And the second thing is you have to consider the denominator and division by 0. So let me start out. I'm just going to put the first thing to consider. The square root of a negative is not allowed in the real number system. So you would take your radicand, which is 3x minus 2. And you would say this needs to be greater than or equal to 0. So let's go ahead and add 2 to both sides of the inequality. We'll cancel this. Let me just drag this over here. We'll say that 3x is going to be greater than or equal to 2. Let me divide both sides of the inequality by 3. This will cancel. And you get x is greater than or equal to 2/3. Okay, let me get rid of this scratch work here. I'm just going to slide this over like this and put that there. And maybe that doesn't line up, so I'll just rewrite first, or you could put number 1 or whatever. Now we have to think about this denominator here. Okay, so this can't be 0. So you're going to say that 6x squared plus 8x minus 30. Let's set that equal to 0 and see what we get. What I would do here, you notice that everything is even. So I would divide everything by 2, just so I'm working with smaller numbers. So let's go ahead and do that real quick. So that would give me 3x squared plus 4x and then minus 15, and this equals 0. Now, can I solve this by factoring? I don't know because I haven't actually worked this problem yet, but I'm assuming that I can. So let me go ahead and set this up. I'm going to put a 3x here, and then I'm going to put an x here. And then I'm thinking about this guy and this guy. Now, this is a minus 15 here, or a negative 15 if you want to think about it like that. Let me go plus negative there, just so that's a little bit more clear. So that means my signs have to be different, right? I need a positive and then a negative. Now, for 15, forget about the fact that it's negative for a moment. It's only 1 times 15 or 5 times 3. So it's not really that many things to check. If you put a 5 here and you put a 3 here, this is going to be 15, and this is going to be 3. Well, 15 minus 3 is 12. So get rid of that. That's not going to work. Now, if you switch the order, and you put a 5 here and a 3 here, well, now you would have 9 and then 5, and 9 minus 5 would be 4. So it looks like that's what we want. Just got to work out the signs. So we would want a plus here and then a minus here. So this right here would be your 9x, and then this right here would be your negative 5x, and 9x minus 5x would be 4x, and then also your negative 5 times your 3 would be negative 15. So this is what we're looking for. Okay, so now that we have the factorization, let me get rid of this, and I'll just move this up here. We will first say that 3x minus 5 is equal to 0. Let's add 5 to both sides of the equation. Get rid of this. We'll say 3x is equal to 5. Divide both sides of the equation by 3. Let's cancel the 3's. And we'll say that x is equal to 5/3. Okay, let me get rid of this. Let me put a comma here and put second. And I'm going to put x is not equal to 5/3. We also have to consider this one. So x plus 3 is equal to 0. Subtract 3 away from each side of the equation. You get x is equal to negative 3. Now, this one is actually not going to be a problem for us. And I'll explain why in a moment. Let me just put a comma here and put x is not equal to negative 3. We're going to get rid of that restriction in a moment because we don't even need it. And I'll explain why right now. So let me get rid of this. You can actually get rid of this one right away. You can't use an x value of negative 3 because of this guy right here. That would give you a square root of a negative number. So you want to just get rid of that one and just say that your domain would be the set of all x such that x is going to be greater than or equal to 2/3. And I'll say that x is not equal to 5/3. Okay, let's close that down. For your interval notation, again, let's use a bracket with 2/3. And then we're going to go up to and exclude 5/3. So I'm going to use a parenthesis there. And then the union with, you're going to use a parenthesis with 5/3 and then go out to positive infinity. Now, again, we can sketch a graph of this guy just to confirm what we found. So if you type in y equals square root of 3x minus 2 over 6x squared plus 8x minus 30, this is what you would get. You can see that the smallest x can be is 2/3. So right there, you get that point where x is 2/3 and then y is 0, right? If you plug in a 2/3 for x, 3 times 2/3 would be 2. And then 2 minus 2 would be 0. Square root of 0 is 0. So 0 over a non-zero number would give you 0. So you get 2/3 comma 0. So the smallest x can be is 2/3. To the left of 2/3, you don't see anything. Then we can have any x value that's larger going out to positive infinity with the exception of 5/3 because that gives me division by 0. Okay, so you see a vertical asymptote here that's created at x equals 5/3. So the graph is going to approach an x value of 5/3, but never touch it. And the same thing here. It's going to approach an x value of 5/3, but never touch it. So here the domain is the set of all x such that x is greater than or equal to 2/3, and also x can't be 5/3. All right, let's take a look at problem 9. So I'll just tell you in advance, this is the most tedious problem in this practice test. We have y equals the square root of 6x squared plus 11x minus 7. This will be over the square root of. You have the absolute value of 2x minus 5, then plus 4x squared minus 2x minus 13. So we have two things to consider. First, in the numerator, you have the fact that the radicand for this square root guy needs to be non-negative. So in other words, we need to solve 6x squared plus 11x minus 7 is greater than or equal to 0. So that's the first thing we need to do. I'm actually just going to grab this and I'm going to paste this in right here. So let's come back up and let's think about the denominator. So now you have the square root operation. So the radicand needs to be non-negative. But we're in the denominator, so you really can't say that it could be 0 because, again, the square root of 0 would be 0. That would give you a 0 in the denominator, and division by 0 is undefined. So you would want to say the absolute value of 2x minus 5 and then plus 4x squared minus 2x minus 13 is strictly greater than 0. So I'm going to grab this and cut this away, come down here, and I'm going to paste this in. And so basically we're solving a compound inequality with the keyword and. Okay, so it has to work in both. So I'm going to start off with this one. It's a little bit easier than this one. So the 6x squared plus 11x minus 7 is greater than or equal to 0. So let me grab this real quick. All right, before we look at this algebraically, I think it's important to look at the graph. So again, you can go to Desmos and just type in 6x squared plus 11x minus 7, or you could also do y equals 6x squared plus 11x minus 7. Don't worry about this part right here. Okay, just type in this on the left. Now, when we look at this graph, we're thinking about where are the x values that produce y values that are either 0, meaning you're on the x-axis, or greater than 0, meaning that your graph is above the x-axis, right? If you're above the x-axis in terms of your graph, all those points are going to have y values that are greater than 0. So we would first look at the intercepts. So that's right here and right here. So that's where y is going to be 0 because, again, you're on the x-axis. So this one right here, you really can't tell from the decimal approximation, but it's going to be -7/3 in terms of the x value. And we'll find that in a moment when we do this algebraically. So -7/3, comma, 0. So that's one x-intercept. The other x-intercept is going to be, you see that's a 0.5. So let's write 1/2 and then comma 0. So we know that this guy would be satisfied where x is -7/3 or where x is 1/2 because you would get 0 is greater than or equal to 0. But it would also be satisfied for any x value that is to the left of -7/3, or you could say any x value that is less than -7/3. So let me say that x is less than or equal to -7/3. Then I'm going to write my keyword or. You could also see that this would be satisfied for any x value that is to the right of 1/2, or you could say greater than 1/2. So let's say x could also be greater than or equal to 1/2. So that's how you could look at this graphically. You could see that any x value that's between -7/3 and 1/2, and I'm excluding both of those, you would be below the x-axis in terms of your graph, right? So the y values are all less than 0 there, so you would not satisfy the inequality in that case. Okay, let's do this algebraically. So let me paste this in here. This is something that I would factor. You always want to try to factor these. It just makes your life a lot easier. So I'm going to factor the left-hand side. So I have a 6 here, which is a little bit tricky to factor because 6 could be 6 times 1, but it could also be 2 times 3. Now, given the fact that I have a -7 here at the end, let me go plus negative here so that's clear. I'm just going to start with 2 and 3 because I think that's more likely to work. I actually don't remember how this factors. So I'm going to start with 2x and 3x. And then for -7, forget about the fact that it's negative. You need a 7 there, so it's only 1 times 7. So I'm just going to put in a 1 here and a 7 here and just see what happens, and I'll work out the signs if it works. So 2 times 7 is 14, and then 1 times 3 is 3. So 14 minus 3 would give me 11. So at this point, I just need to put a minus here and a plus here. So that's going to give me 2x times 7. That's 14x. So let me show this. This would be 14x. And then -1 times 3x would be -3x. 14x minus 3x, that's 11x. Okay, so that's exactly what we want. All right, so now that we have this guy factored, you can get rid of this form right here. I think it's just easier to work with this form. You are going to find your critical values. So you're going to replace this inequality symbol with equals. So we would have 2x minus 1, that quantity, times the quantity 3x plus 7. And we'll set this equal to 0. Let me slide this down and out of the way. So you would have 2x minus 1 is equal to 0. Or you would have 3x plus 7 is equal to 0. Let me get rid of this, slide this up. So let me add 1 to both sides of the equation here. That would cancel. You get 2x is equal to 1. Divide both sides by 2, and you're going to get x is equal to 1/2. Remember, we found on the graph that x equals 1/2. That was the x coordinate from one of the x-intercepts. So when x is 1/2, we know y is 0. So let me get rid of this and drag this over here. And the other x-intercept, if we subtract 7 away from each side of the equation, we'll cancel this. We get 3x is equal to -7. Divide both sides of the equation by 3, and you're going to get that x is equal to -7/3. So we saw that point that was -7/3 for the x value, comma 0 for the y value. That was another x-intercept. So let me put x is equal to this -7/3. Okay. So we're going to use this to break our number line up into these regions. So you're going to take -7/3 and put that on the left. And then you're going to take 1/2 and put that on the right. You can get rid of this at this point. You don't need it anymore. And so you're going to say this is A, this is B, and this is C. Now we looked at the graph. And again, we found that anything to the left of -7/3 or anything less than -7/3 would work. And then we found that anything to the right of 1/2 would work. So we are expecting that things in region A would work, things in region B, right, between these two numbers, that's not going to work, and things in region C, that's going to work again. So let's come back down here and verify that. So in this particular case, if I think about -7/3, that's -2 1/3. So let's just pick maybe -3. So let's plug that in there and plug that in there. If you want to go faster here, you can just do a sign analysis. So 2 times -3 is going to be -6. And then -6 minus 1 is going to be -7. Let me write this over here. So this is -7. And then times over here, 3 times -3 is -9. And then -9 plus 7 is going to be -2. So a negative times a negative is a positive, right? So we know this would be true. This would end up giving me 14, and 14 is certainly greater than 0. So get rid of this, and you could say that this is true. And again, we saw that with the graph. So for things in B, they shouldn't work, right? So I would pick 0. It's really easy to work with. So if you plugged in a 0 there and you plugged in a 0 there, you'd be left with -1 times 7, which is -7. A negative is never greater than 0 and it's not equal to 0. So things here are not going to work. So you could say this is false. All right, in region C, I would just pick 1. So let's plug that in there and then there. So 2 times 1 is 2. And so I would have 2 minus 1, which is 1. And then times 3 times 1 is 3. And so 3 plus 7 would be 10. So a positive times a positive is a positive, and that's always going to be greater than 0. Or you can just say 1 times 10 is 10. 10 is greater than 0, so this is true. So to get my solution here, consider the fact that you have a non-strict inequality. So your critical values will be included because they will satisfy the inequality. You would have 0 is greater than or equal to 0 in each case, which is a true statement. So we would say that x is less than or equal to -7/3. And then or x is greater than or equal to 1/2. So exactly what we found from the graph. So let me grab this real quick, and I'm going to cut it away. And I'm going to come back up here and paste this in. And I'm just going to arrow over to this. So this is the first solution here. And now we have to figure out this one. And before we go any further, I just want to show you this graphically so we know what to expect. Once again, you can just type the left side into Desmos if you want to get a picture on your own. And basically what you're thinking about would be, what are the x values that are going to produce y values that are greater than 0? So you're looking for the graph to be above the x-axis, right? Because the x-axis, again, that's where y is going to be 0. So here, let me do this in a different color. This is an x-intercept. So we could say that this occurs at -1, 0. And then this is an x-intercept. So that would occur at 2, 0. Where is my graph above the x-axis? Well, anything that's going to be an x value that's less than -1 or to the left of -1, if you want to think about it that way, the y values are going to be greater than 0. So you could say here that x would be strictly less than -1. Remember, -1 is not going to work because this would make this 0. So 0 is not greater than 0. That would give you a false statement. So then you would say, or, additionally, we could think about the x values that are greater than 2 or to the right of 2. And so those would produce y values that are greater than 0. You can see your graph is above the x-axis. So here we would say, or x is greater than 2. So this is what we would expect to find. So let's go ahead, and I'm just going to paste this in. Remember how you want to do this. If you have an absolute value expression involved in this problem, what you want to do is split this up into different cases. So first you want to say 2x minus 5. This is equal to 0 where? So I'm going to add 5 to both sides of the equation. I'm going to cancel this and say this is 2x is equal to 5. Divide both sides by 2, and you're going to get that x is equal to 5/2. Okay, so if x is 5/2 or anything larger than 5/2, then what I want to do is just drop the absolute value bars. Okay, so I just want this guy right here, like this. Let me get rid of that. And then if x is less than 5/2, what I want to do is drop the absolute value bars, but I want to replace it with its opposite. So the negative of 2x minus 5 like this, and then plus 4x squared, and then minus 2x, and then minus 13 is greater than 0. Okay, let me grab these both and come down here. I set up a little table already. Don't know if this is going to fit. So let me see if I can write it a little bit more neatly. So this one, I'm just going to distribute it. I know it's hard to read right now, but I'm going to write it out here. So negative of 2x minus 5, that quantity, that's negative 2x and then plus 5. And then you have plus 4x squared, and then minus 2x, and then minus 13 is greater than 0. Okay, let me get rid of this, and then let me write this one in here. So this one is 2x minus 5, and then plus 4x squared, and then minus 2x, and then minus 13 is greater than 0. Okay, remember how this works. You're going to solve this inequality, and you're going to think about, in this region, Does that fit? Okay, so if you get something outside of that region, you have to reject it. So this one, I'm just going to simplify it first. So it looks like negative 2x minus 2x would be negative 4x. So let's write 4x squared minus 4x. And then you would have 5 minus 13. And that's going to be negative 8. And this is greater than 0. Okay, I'm just going to erase this and slide this up. Actually, instead of sliding this up, if you divide everything here by 4, you're going to have a much easier time working with this. So this would be x squared, and then minus x, and then minus 2, and that is going to be greater than 0. Okay, let me get rid of this, and let me copy this real quick, and I'm just going to paste this in here. So let me put a negative 1 in there. I'm just going to factor this to make it a little bit easier to work with. This is an x, and this is an x. You need two integers that sum to negative 1 and have a product of negative 2. So you can go negative 2 and then positive 1. Okay, so I'm just going to say that this is the quantity x minus 2 times the quantity x plus 1 is equal to 0. And so you would say x minus 2, this factor here, is equal to 0, or x plus 1 is equal to 0. So this guy right here, you just add 2 to both sides, and you get x is equal to 2. Over here, you would subtract 1 away from each side, and you would get x is equal to negative 1. So let's put a negative 1 there and a 2 there. Let's get rid of this, and you can just test. We'll say this is A, this is B, and this is C. So if I plug in, let's say, a negative 2, let's try that for region A. Let's see what we get. So plug that in there and there. So negative 2 minus 2 is negative 4. And then here, negative 2 plus 1 is going to be negative 1. So negative 4 times negative 1, we know that's a positive. It would be a positive 4. And so that is going to be greater than 0, right? So this is 4 is greater than 0, which is true. So we'll say this is true. Okay, so for region B, I would just pick 0, and obviously that's not going to work. If you plug in a 0 there, and you plug in a 0 there, you're going to get a negative times a positive, right? You'd have a negative 2 times a positive 1. That's a negative 2, and a negative is never greater than 0. And specifically here, you would say that negative 2 is greater than 0 is a false statement. Okay, so I'm just going to say this is false. Does not work. All right, for region C, you're going to see things work again, so let's pick 3. So put that in there and then there. So this would be positive and this would be positive. So a positive is always greater than 0. So this is true. But if you want to work this out, 3 minus 2 is 1. And then 3 plus 1 is 4. And of course, this would be 4. And 4 is obviously greater than 0. So it's a true statement. Okay, let's get rid of this. Now the critical values don't work here because this is a strict inequality. If you plugged in a negative 1 or if you plugged in a 2, you would get 0. And 0 is not greater than 0. That's a false statement. So you would say that x is less than negative 1 or x is greater than 2. You have to make sense of this because, again, I'm in a region where x is strictly less than 5/2. So what you want to do, you can actually get rid of this. You don't need it anymore. You can say x is less than negative 1, so that's okay. Then you could say, or you're going to say x is greater than 2 and less than 5/2, right? Because you can only include things in this interval when you solve things this way. Okay, let me get rid of this. So this is what we call partial solution at this point. I have to look at this guy, and then I'll try to merge the two. So for this one, it's going to simplify pretty nicely. 2x minus 2x, that's going to go away. So you're just going to have 4x squared, and then negative 5 minus 13 is going to be negative 18, and this is greater than 0. Let me get rid of this, and let me divide everything here by 2, just to make it a little bit simpler. So this would be 2x squared, and then minus 9 is greater than 0. Okay, let me get rid of this. And let's think about how we could solve this. So I'm just going to grab this and go to a different sheet. So the first thing I'm going to do is replace this inequality symbol with equals. So let's suppose that we had 2x squared minus 9 is equal to 0. We're going to add 9 to both sides of the equation. Get rid of that. You're going to get 2x squared is equal to 9. Let me actually erase things as I go. I'm going to divide everything here by 2. Cancel this with this. And you're going to get x squared is equal to 9/2. You're going to use the square root property here. So if x squared equals k, then x equals plus or minus the square root of k. So x here is equal to plus or minus the square root. I'm going to write this as the square root of 9 over the square root of 2. The square root of 9 is 3. So this would be plus or minus 3 over the square root of 2. So most people will, again, rationalize the denominator. So you multiply by the square root of 2 over the square root of 2. So this would be plus or minus 3 times the square root of 2 over 2. Okay, so those are the critical values. If I plug in 3 times square root of 2 over 2 in here for x, I would get 0. And of course, 0 is not greater than 0. Or if I plugged in the negative of 3 times square root of 2 over 2 in for x, well, then I'm going to get 0, and 0 is not greater than 0. Now, I'm going to put this here. So negative 3 times square root of 2 over 2. And I'm going to put this here, 3 times square root of 2 over 2. If we were solving this as a regular quadratic inequality, then you would need to set up a, b, and c. But here I actually don't need to do that because I'm only working in the interval where x values are greater than or equal to 5/2. This guy right here, if you think about it, is about 2.12, let's say. So really, I could just check things in this region and see if they work. If they do, what I'm going to do is say that that part of the solution is x is greater than or equal to 5/2. So let's just go ahead and check things here. You could pick something like, let's say 3 if you wanted to. So I would have 2 times 3 squared, and then minus 9 is greater than 0. So 3 squared would be 9. So this would be 2 times 9 minus 9 is greater than 0. 2 times 9 is 18, so 18 minus 9 is greater than 0. And this would be 9 is greater than 0, which is true. So I can say that x values that are greater than 3 times square root of 2 over 2 will work in this inequality. Again, you don't need to check this and you don't need to check this because no matter what you get, it's irrelevant to what you're working on. So let me come back up and I'm going to put x is greater than 3 times square root of 2 over 2. And I'm going to merge that with the fact that this is only valid for x values that are greater than or equal to 5/2. So this right here, this 3 times square root of 2 over 2, this is less than 5/2. So what I'm going to actually do is just say, well, this is x is greater than or equal to 5/2. Let me get rid of this and let me move this over here. Okay, so now you're going to merge these two solutions here using the keyword or. Okay, so I'm going to say or like this. And basically what that is going to give me is that x is less than -1, then or you would have that x is greater than 2, right? Because here x is greater than 2 and less than 5/2. But then you have the keyword or here that connects this one where x can be 5/2, so that includes that value, or anything larger. So basically you would say x is less than -1 or x is greater than 2. So let me go ahead and grab that real quick. And I'm just going to revisit this where we started, where we said we would expect x is less than -1 or x is greater than 2. So we found that. Let's come back up. All right, let me paste this in here. And I think for the purposes of what we're going to do, I'm just going to work with the solutions. And this is really not that bad. You're using the keyword and to combine things. So first I would think about this in terms of what are my less than statements telling me? So this is a less than or equal to, and this is a less than, but you're thinking about x values going to the left. So what's the most restrictive? Where you're looking for the guy that's the most to the left or the most negative here, because you have an x that is less than or equal to -7/3. Is -7/3 further to the left than -1? Yes, right? So you want to pick the one that is most restrictive so that it covers both of them because it has to work in both. So I'm going to say that this is x is less than or equal to -7/3. So let me put that like that. Then I'm going to go or. When I think about these greater than statements, you have an x is greater than or equal to 1/2, and then you have an x is greater than 2. Again, if I want it to work in both, I need something that's the furthest to the right. So the bigger number, 2 is bigger than 1/2, so I'm going to use x is greater than 2 here. Okay, so this is what I'm looking for. So I'm just going to grab this. We'll come all the way back up here. So we're ready to write our domain. So the domain is the set of all x such that x is less than or equal to -7/3. Then or x could be any value that's greater than 2. Okay, if you want to write this in interval notation, we'll go ahead and say that coming from -infinity, going up to and including -7/3. So you want a bracket here. And then the union with, it could be anything larger than 2. So 2 would be excluded, anything going out to +infinity. All right, let's verify what we found algebraically using our graph. So when we look at our graph, again, you can get this on Desmos, y equals the square root of 6x squared plus 11x minus 7. This would be over your square root of the absolute value of 2x minus 5, then plus 4x squared minus 2x minus 13. So we can see that over here, this point is going to be -7/3, comma, 0. So -7/3 is okay for x, and then any value that is to the left of that, or you could say less than that, that would work. Then you can see that there's really no x value here up until we get to a value for x that's greater than 2. 2 itself is going to be excluded. We have a vertical asymptote at x equals 2. So this graph will approach where the x value is 2, but it's never going to actually get there. So we can see that x can be anything that's greater than 2, but not 2 itself. So this verifies the domain. We have the set of all x such that x is less than or equal to -7/3. So anything here are going to the left, or x could be any value that is greater than 2. All right, let's take a look at problem 10. So here we're going to have y is equal to the square root of 35x squared minus 58x minus 9. This will be over the square root of x squared minus 2x plus 1. Okay, so once again, I'm thinking about this square root operation in the numerator, and the radicand here needs to be non-negative. So I would write that 35x squared minus 58x minus 9 needs to be greater than or equal to 0. So we need to solve that. Let me grab this real quick, and I'm just going to paste this right here. Let's go back up and think about the other part here, which is in the denominator. You have a square root operation, so the radicand is x squared minus 2x plus 1. So again, this needs to be non-negative, so let me first start by saying x squared minus 2x plus 1 is greater than or equal to 0, but we're in the denominator here. So if this was equal to 0, you'd have the square root of 0, which is 0, and you can't have division by 0 that's undefined. So you want to tighten that up and say it's strictly greater than 0. Okay, so let me get rid of this, and let me grab this and come down here. I'm going to write the keyword and then I'm just going to paste that in. This one's really easy to solve. The left side here is a perfect square trinomial. We'll do that one last. Let's do this one first. It's a little bit more challenging, so let me grab it, and let's paste this in real quick. Again, you can go to Desmos or whatever online calculator you want to use. Just type in the left-hand side here. So you can go y equals, or you can leave it off and just put 35x squared minus 58x minus 9. So just the left side, okay? Don't put this in. So you're going to produce this graph, and what you're looking for are the x values that are going to produce y values that are either 0, so that means you're on the x-axis, or greater than 0, so that means your graph is above the x-axis, right? That's where your y values are greater than 0. So thinking about on the x-axis itself, the x-intercepts, this point right here is hard to tell because we have some decimals involved, but this is going to be -1/7. So -1/7 and then comma 0. So that's an x-intercept, and this x-intercept here, this is going to be 9/5 and then comma 0. Let me make this a little bit better here. Now, you can tell that basically any x value that's to the left of -1/7, or you could say less than -1/7, is going to work, right? So the y values there, they're going to be greater than 0. Your graph is going to be above the x-axis. Additionally, you can see that x values to the right of 9/5, or you could say greater than 9/5, that's going to work as well, right? So the y values there are going to be greater than 0. Your graph is going to be above the x-axis. So I can already give myself a little solution here. I can say that x could be less than or equal to this -1/7, or x could be greater than or equal to this 9/5. So this is what we're expecting to get. So let me go ahead and grab this real quick and come down here, and we'll just slug it out and do this the algebraic way. I know a lot of people don't like this, but I think it's good to get some practice. Okay, the first thing I'm going to do here is just factor the left side. So really this is not that bad, although it looks kind of terrible. So for 35, you either have 1 times 35. That's unlikely to work, so I wouldn't start there. And then you have 5 times 7. Now, I've already factored this, so I know that 5 times 7 works. But again, if I hadn't factored it, I would start with 5 times 7. So I'm going to go 5x here, and then 7x here. And then I need to think about this position and this position. Now, this right here is a minus, okay? So if the final guy is a minus, that means I have different signs. And when I work things out, I'm going to imagine that this is positive, and I'm going to do a subtraction. So with 9, again, forget about the fact that's negative. I'm going to think about 1 times 9 or 3 times 3. If I use 3 times 3, it's really easy to check. You just put that in there and there, and you really can't alternate that because it's the same number. Well, when you go to the outer and the inner, again, you want to subtract things. Let me just show you. So 5x times 3 would be 15x. And then 3 times 7x would be 21x. Just think about a subtraction. It doesn't matter what the signs are going to be. Just think about a subtraction. 21x minus 15x would be 6x. And so this isn't going to work, right? You need negative 58x. So let's get rid of this and get rid of this. So it has to be 9 and 1. Now, just for the sake of going through everything, let me put the 9 here and the 1 here. This isn't going to work, but we're just going to go through it. So this right here would be 5x times 9, that's 45x. And this right here would be 1 times 7x, that's 7x. Again, do a subtraction because you're going to have different signs. So 45x minus 7x, that's going to be 38x. So we know this isn't going to work. Okay, get rid of this, and I'm going to switch this up. And now it's going to work. So this right here is going to be 5x, and this right here is 63x. So again, you always want to think about if this is a negative here, do a subtraction and see if you can get to this guy in terms of absolute value. So 63x minus 5x would be 58x. Forget about the fact that it's negative. We don't care about that right now. We can make the signs work by putting a plus here and then a minus here. So the end result here would be 5x, and this would be negative 63x. And then negative 63x plus 5x would give you that negative 58x. Okay, so we found our correct factorization, and now we're pretty much ready to roll. Let me get rid of this. We don't need it anymore. And so I'm going to go 5x minus 9, that quantity, times the quantity 7x plus 1 is equal to 0. Let me slide this down here and out of the way for a second. So we are going to solve 5x minus 9 equals 0, then or 7x plus 1 equals 0. Let me get rid of this. And this one, I would add 9 to both sides. That would cancel. You get 5x is equal to 9. Divide both sides by 5, and you get x is equal to 9/5. So let me get rid of this. And let me put 9/5 here. And then I'm going to subtract 1 away from each side here. This cancels. We're going to have 7x is equal to negative 1. Divide both sides by 7. You're going to get x is equal to negative 1/7. Okay. Let me get rid of this. And now we can set up some intervals. So A, B, and C. If we go back to what we looked at, we know that in region A, it's going to work, right? So anything that's to the left of negative 1/7, right? Negative 1/7 works, but don't worry about that for right now. Region B, so that's between negative 1/7 and 9/5, that's not going to work, right? These y values are going to be less than 0, right? The graph is below the x-axis. And then in region C, it's going to work again, right? So this is anything that's greater than 9/5. So let's come back down. We know what we should expect. And we're just going to pick some values. So for A, let's pick negative 1. I think that's easy to work with. And plug that in there and there. So 5 times negative 1 is negative 5. And then you'd have minus 9. And so negative 5 minus 9 is going to be negative 14. So this would be negative 14. And then times 7 times negative 1 is negative 7. And then negative 7 plus 1 is going to be negative 6. So again, this is a negative times a negative, which is a positive. We don't actually care what the result is because a positive is always greater than 0. So you can just say this is true. Just in case you wanted to know, you could punch that into your calculator and you would get 84. Okay, so 84 is clearly greater than 0. So let's get rid of this. All right, in region B, I'm just going to pick 0. It's very easy to work with. And very quickly, you can see this isn't going to work, right? So you basically have negative 9 times 1, which is negative 9. And then negative 9 is a negative number, so it's not greater than 0. It's certainly not equal to 0, so this is going to be false. Okay, for region C, let's just go ahead and pick 2. I think that would work out pretty nicely. So let's plug that in there and there. So 5 times 2 is 10. 10 minus 9 is 1. So this would end up being 1 over here. And then 7 times 2 is 14. 14 plus 1 is 15. So you'd have 1 times 15, which is 15. Of course, it's a positive number, so it's greater than 0, so this is true. Okay, let me get rid of this. And let's go ahead and write our solution. So because we have a non-strict inequality here, negative 1/7 and also 9/5 will work. Because again, in either case, you'd have 0 over here. And if you get 0 is greater than or equal to 0, that's a true statement. So let's go ahead and say that x is less than or equal to negative 1/7, or x is greater than or equal to 9/5. And that's exactly what we found from the graph. So let's go ahead and grab this real quick. And let me slide this down here. And I'm just going to paste this in. And actually, you can get rid of this and just keep this solution here. I'm going to look at the solution for this. So let me cut this away. And I'm just going to come down here. You really don't have to do much work for this one. As you can see, when you think about this, if this was a greater than or equal to 0, then the answer would be all real numbers, okay? And the reason for that is very simple. If you factor this guy, this is a perfect square trinomial, so it factors into a binomial squared. This is going to factor into x minus 1 quantity squared. If you said, where is this greater than or equal to 0? Well, this is true for all real numbers. And that's because of this squaring operation right here. So it doesn't matter what you plug in for x. you subtract away 1. Once you square it, if it's a negative, it becomes a positive. If it's 0, it stays 0. And basically, if it's a positive, it stays positive. So no matter what you plug in there, it will always be either 0 or some positive number. So it will always be non-negative, and you can see that from the graph. The problem is we don't actually have that. We have a strict inequality here because this guy right here was the radicand for your square root, and that was in the denominator. So it can't actually be greater than or equal to 0. It has to be greater than 0 so we can avoid division by 0. So what we actually have to do is just think about where this guy would be 0, and you can see that's going to occur when x is 1. So 1, 0, basically that is your x-intercept there. So you could think about this as just saying, let me go back to the x minus 1 quantity squared. Where's that equal to 0? Well, by the square root property, you can say that x minus 1 is equal to plus or minus the square root of 0. And of course, the square root of 0 is 0, so you can get rid of the plus or minus. So you get x minus 1 is equal to 0, add 1 to both sides of the equation, and you get x is equal to 1. So this is the only value for x that is going to make this guy a false statement. Any other value for x, a negative value, 0, a positive value, whatever you want, if you plug it in, you're going to get something that's greater than 0. Only at x equals 1 will you get a value of 0. And again, you can see that from the graph. So what I would say for this one, to solve this, is to say that x is less than 1 or x is greater than 1. Kind of a weird way to write that, but basically you're saying that x could be any value less than 1 or greater than 1, so it can be anything except 1. So let me grab this, and let's come back up here and put these two together. Okay, so I'm just working on these two solutions, and I have my keyword and. So I'm just going to think about the less than statements first. So here you have x is less than or equal to negative 1/7, and here you have x is less than 1. So you got to think about which one's going to be more restrictive. Which one, in terms of these values, either negative 1/7 or 1, is furthest to the left? Well, this one is because it's a negative value. So in my answer, I want to put x is less than or equal to negative 1/7. Then I'm going to put or. Think about these two greater than statements. So x is greater than or equal to 9/5, and then x is greater than 1. Which one is the furthest to the right now? So which number is going to be bigger? That's going to be the more restrictive value. So I'm going to go ahead and say that it's going to be 9/5 because that's 1.8 as a decimal. So I'm going to put x is greater than or equal to 9/5. So you're basically taking this solution here from the first inequality that we solved. So let me go ahead and grab this, come back up and paste this in. Let me slide down here and we'll write our domain. So the domain is the set of all x such that x is going to be less than or equal to negative 1/7, or you could also have x as greater than or equal to 9/5. Okay, let me close that down. And we'll bring this up here. And basically at this point, you could write it in interval notation. So coming from negative infinity, going up to and including negative 1/7. So I want a bracket there. And the union with, you're going to include 9/5. So I put a bracket there. And then going out to positive infinity. All right, let's confirm what we did using a graph. So here we have y is equal to the square root of 35x squared minus 58x minus 9. This is going to be over the square root of x squared minus 2x plus 1. So looking at the graph, you can see that this point right here, this is an x-intercept, and it occurs at negative 1/7, 0. So we can see that that value is included, and then anything to the left, or you could say anything less than that. So that's this part right here. X is less than or equal to this negative 1/7. Then over here you have this guy, another x-intercept. So that occurs at 9/5, 0. So 9/5 is included as an x value, and then anything to the right, right? So this part right here is x is greater than or equal to 9/5. So this verifies what we found. We could say our domain is the set of all x such that x is less than or equal to negative 1/7, or x is greater than or equal to 9/5.